Today we're going to talk about the new identification method that is called subspace methods. This is quite different from the concept we've seen before in the previous chapter, that is statistical estimation. Subspace method is more relevant to least square estimation. It applies the concept from orthogonal projection. It uses the tools. It uses geometric tools dealing with projection on matrices, and it provides a scheme for estimation of state space parameters, state space model parameters. So in this chapter, we're going to see the concept and the tools we need. All right. And we take a look at two popular algorithms in subspace identification that is called PO. I usually call it MOSE, but I'm not sure. Is that the right way to pronounce? Okay. And the last one is N4SID. Okay, this is an algorithm that is implemented in subspace identification toolbox as well. Okay. In this video clip, probably I give an introduction. Okay, and maybe I jump to the Matlab examples. Okay, and then we come back to the theoretical parts again, the concept behind. So this method relies on the model parameterization in state space form. So we consider discrete time, of course, time invariant, and it is a stochastic system. Okay, which means in the state equation we see a process noise W. Right. In the output equation we have V, which is a sensor noise. All right, we call it sensor noise. This is called process or state noise. All right. What do we assume about this noise? They have covariance matrix. For W, covariance is Q. For V, the sensor noise covariance is R. It also has cross covariance between these two noise that is given by S. All right. With the delta function, it means that these are white noise. All right. The correlation of WT and WS is 0 when T is not equal to S. All right. And when and the covariance is given by as I said, Q and R. Okay. We're dealing with MIMO case, which means everything here are assumed to be vectors. U, the input, the output, and of course the state variable is typically a vector. The dimension is given here, M and P. So for input, for output and input. Sorry, for output, for input. Sorry, M is the number of input, P is the number of output. The problem statement is that we are only given the input-output data set for finite samples. What we're going to do is we find an appropriate order n of the state space model, and we aim to estimate ABCD, the system parameters, and also the noise covariance QRS. Okay, this is the list we're going to estimate. So let me explain an overall scheme of a subspace method we consider here. As I mentioned, that the main process will be conceptually explained according to PO-MOSEP algorithm. Okay, the scheme starts from deriving data equation. Okay, this is very straightforward. You consider state space equation. You write down the output equation at time t plus 1 and blah blah blah. All right. So conceptually, we see that the output y depends on x, the state variables at various times. It depends on you, and this is depends on input, this is depends on state, and depends on the noise. Both because y is a function of x, right? Y is corrupted by sensor noise, but y, because y is also a function of x, but x is corrupted by the process noise. So what you see at the output equation, there will be a mix of effects from both state and sensor noise. Okay, here's these are the noise term. All right, that is the combination of state and process noise. The concept of estimate these system parameters starts with removing the effect from input. All right, we're gonna take a look at the data equation. What we see here is that the thing is you only have the information about u and y. All right, you only have the profiles, the time series, the data. But then what's the system parameters hidden in here? We will explain, we show you the data equation like in detail later, but what we can say right now is that these two matrices, OS and tau S, these contain the system parameters A, B, C, D. So what you're going to estimate is kind of hidden in OS and tau S. All right, Y and U, these are given. All right, but the term is unknown. The uncertainty V, that's from noise. Okay, so at the end we try to use the given information, and at the end we would like to jump to this box G equal OST. That's our goal. Whenever we can end up with this equation, because we know that the system parameter is hidden in OS, all right, we're gonna use the process of SVD. But before, in order to reduce the data equation to the one in the blue screen, we need to is remove the effect from input U, and remove the effect from the noise. All right, and these two processes in the brown boxes, these can be done by using the concept of orthogonal projection. Okay, all right, and once we get the equation in the blue box, all right, so typically we're gonna get the matrix G in as a fat. The matrix OS is gonna look like this. All right, it's gonna be something like this. All right, the number of rows in OS and the number of rows in G will be equal. And then that's why we need to perform an SVD here. As you will see, why SVD factorization takes place in this method. All right. Once we can estimate OS, what is OS? OS is actually extended observability matrix. If you can recall, observability metric is going to be CA CA to the n minus 1. This is a metric that indicates the property that is called observability. All right, if you can recall, if the system is observable, it means from the measurements of Y, you can estimate the initial state. All right, the information from the output is sufficient to estimate X naught. All right, and if you get X naught, you can estimate the whole thing, the whole state variable xt. All right, and if you can recall, if the rank of observability metric is n, which is the model order, all right, the system is called observable. All right, what we consider in this method is extended observability matrix, where you extend this n to be, any integer s. So basically, what you're gonna have is you're gonna have C, CA. All right, the OS metric contain S blocks. All right, each block has a size, has the same number of row as the matrix C, which is the number of, which is the dimension of the output Y. Okay, so I state the dimension here. The matrix OS, you see that plays an important role in subspace ident, because you see that, as I said here, OS contains system matrices, system parameter, and C and A. If you can estimate OS, because in the next step, you can estimate A and C. In the lecture, we will explain step by step what's the mathematical, what's the concept behind. But let's see as an overview here. Once we can estimate A and C, right, from the mathematical description of the state space dynamics, we can estimate B and D eventually. And once we can get everything A, B, C, D, we can estimate the noise covariance. All right. So this is an overall scheme, and two important tools are orthogonal projection and SVD factorization. These will be some important roles. Okay. All right. Before I explain, so we need to explain. Maybe we need to review a bit about orthogonal projection. But before doing that, I would like to jump to some numerical examples right away. So here I have some easy example. We have state space model of DC motor. Okay, and we're gonna explain one of the main algorithm that is called N4SID. Remember, please be reminded that there are many algorithms regarding subspace method. Right? We give you examples of one, right? And also we're going to explain a customized algorithm in subspace ident as well. So two models, DC motors and mass spring models. All right. So let's start with the first one. Take a look at the equation in the black color. I hope everyone recall. Let's review a little bit. When you have a DC motor system, all right. So the DC motor, what is the input and what is the output? Sitipak? Output, can you specify the output first?
Output is the angular position and angular velocity.
Right. It can be either one of them, or it can be both of them. It's up to you, right? Angular velocity. I call it theta and omega, and the relation of these two guys are that omega is theta dot, right? The derivative. Okay. Ping, what is the input of this system?
It's a voltage.
It's a voltage, right? Apply at the at the electrical part of the system, that is a armature circuit, right? Okay. In this equation, in this representation, I mean, if you can recall how we can derive the dynamical equation, you will see that the state variable is actually theta and theta dot. All right, when we write the system, when you select y to be angular velocity, the mod. Sorry. Here in this slide, I select a y to be motor angle. Okay. the system is second order. Okay, as you see here, second order. And as you see from the matrix C here is 1, 0, because you define Y to be a mortar angle. And the the structure of A, B, this is a matrix A, B, C, sorry, A, B, C, D. There is no D in here. There is no D in here. Now let's take a look at this one. This one, UT is the electrical voltage, right? This one is the load torque. I use tau L. You can think of load torque as disturbance, right? As uncertainty term, as a state noise as well. And we model some sensor noise in here. There is no feed-forward term of the input in the output equation, right? There is no UT term in Y in the equation of Y. Sorry. All right. This is continuous time state space equation, and what you learn from the sample data system class, from the digital control system, you can transform continuous time, this state space model, into the discrete time using several methods. And one of them is one of them, which is a simple one, is called zero order Hall. All right. Which means that which assumes that, what's the principle of zero order Hall method, Sitipak?
To transform the continuous time to discrete time.
I know, but what is the principle of zero order Hall? Because there are other methods as well.
They will hold the signal.
Hold what?
Hold the signal for a constant value in a certain period. That is sampling time.
They will hold input. The input is assumed to be held constant, right?
Yeah.
So this is suppose this is your sampling time. It's assumed to be piecewise constant. The input. All right. After we use that method and transform into the discrete time model, we get you get the equation in the blue line. Okay. The thing is that the order is still the same. Continuous time of second order, when you transform into the discrete time, is a second order also. And I forgot to mention that all the terms you see here as a tau B1 and B2, these contains system parameters like initial resistance in the armature circuit, torque constant Ka, and this is the back EMF constant Kv. All right, if you can recall the concept of DC motor. Say. So tau B1, B2 are basically a function of this guy. All right, and if you look at the discrete time state space model, again, this is your A in discrete time, your B. All right, the whole thing is kind of disturbance. This is your C. All right, the matrix C in the discrete time will not change, right, from the continuous time. What we would like to do is to this, of course, again, we we have a profile of YT and UT in a discrete time format, right? Because UT start from 0 to big N. And we would like to estimate the system parameters. Here I use input electrical voltage as the one given in this. It's a pulse. Not sure if I generate PRBS or what. Okay, so let me, I need to check the description, but I mean, it's waveform is given like this. And even though in this equation we know that even though we know that this equation has the output as motor angle, you can also see that if you want the output as the motor velocity, what would you do? What would you change in the system equation? Napat?
We change the C matrix to be 0, 1.
Yes, very good. Okay, we change the matrix C to be 0, 1. The system, I mean, even though we change the description of the output, right? But the order of state space model is the same, because we need two state variables in order to explain system dynamics. Okay. So even though I say that the motor the output is motor angle, you can change it to motor speed as well. And that is actually the case when we collect the data from the experiment. This is the DC motor we use in the lab scale in our control system lab. You will get to see this lab if you take the course 436. Okay, this coming second semester. So so the real thing, so this is the real experiment, is you actually design this waveform on the computer, and of course the computer and the lab are connected by data acquisition system that has, A to D, D to A board. So when the input that is designed in the discrete time manner convert, D to A back to the physical system move the DC motor, all right, the speed, okay, change up and down like this this waveform, and this is what we collect, this is what we measure. So basically, I'm saying that in our lab, the real experiment, we measure the motor speed. Okay, we measure the motor speed, and even though we know that the equation, the dynamical equation we derive here, is a second order, all right, but in the estimation process, so let's pretend that, let's see the results as we vary the model order. So I start from n equals to 1 to all the way to 10. Okay, and just use the system identification toolbox. Okay, and it calculates the fit %. So this is a measure that suggests how well you can estimate the target. This is the real output. This is y hat from your model, from your state space model. I think it's normalized by the error from using the average. Okay, so this is the fit %. So you see that the higher the better. The higher the better your model is. So model order 1. Model order 1, the fit % is about 32. For second order, the fitting increased significantly. All right, and after that second order, third order, it seems to be in the same range. All right, and this is the amplitude fitting after the fitting. Okay, the gray one is the measurements. You see that the blue one is the one from the first order. That doesn't seem, it seems to have a large bias, and that agree with the fitting value as well. Okay. Okay, here's a process. Here's a process along the way. In order to estimate a subspace, in order to estimate system parameters using a basic algorithm, you can call S4 SID. Okay, and when you call S4 SID to estimate the model order in some range 1 to 10, the algorithm, the method will actually shows a window that suggests a quantity that associated with the model order is the log of singular value of which metric. I will explain it later, but let's just say at this step is let's just say that if you can recall the singular value of a matrix X, you know that first of all, what is a singular value? It is the eigenvalue of City Park.
Of X.
No. Singular value. Napat.
I can't remember.
Okay. X transpose X, right? X transpose X with the square root. So because I mean there's a background, right? I think you need to review, but basically singular value are all non-negative. And that is possible because X transpose X is always a positive semi-definite. All right. So when you calculate the singular value, you can sort all of them. That's okay. Probably you sort it in such a way that the first one is the biggest one, right? And all the way to sigma n. Okay. And so this is X is a matrix. I mean, singular value can be applied to rectangular matrix as well, but okay, if a matrix X is m by n, what is the size of X transpose X? Ping.
It is n by n.
Say it again.
N by n again.
Not sure if I clear if I hear you correctly. Like n by p. If X is n by p, what is the size of X transpose X?
X transpose X is p by p.
P by p. So how many singular values are you going to find?
They are p.
They are p. Okay. So there's a fact that the number of non-zero singular value determine what? The number of singular value that is non-zero determine the rank of X. Okay, that's a fact. Okay, please review. So okay, so to explain this plot, so there's going to be a fact. Okay, that I will explain in the concept of subspace method, but this singular value is from a matrix, and the rank of that matrix is associated with the model order n. So that's why when you when the system when the method, right, when the algorithm calculate the singular values, we focus on the significant ones, right? Because the large singular values, the number of large singular values determine the rank of the matrix, and from the concept of subspace, the rank of that matrix is associated with the model order. So from the plot, from the GUI, okay, the red bar is the one suggested by the algorithm, by the N4 SID. Okay, because the singular value at the model of third order is very significantly large compared to this one. Okay. So this is the one suggested by the GUI, even though you know that when you derive the dynamical equation, like from the concept of physics and circuit and everything, right? You know that it's a second order, but of course the algorithm suggests from the data-driven approach. And here, as a user, you can decide yourself if you're gonna use the one suggested by the algorithm, or you can specify yourself, select another one. You can select second order as well. Okay, but thing is, you shouldn't pick the first order because the singular values at the order at the second order and the third order, these singular value are still significantly high. Okay. And okay. So basically, you can call N4 SID by varying N from 1 and 2 to 10, which means you're gonna get model at different orders, estimated model of first order, second order, all the way to the 10th order. And I select 4 of them, and I plot the impulse response. This is the impulse responses of a estimated model. And as you can see, they agree with the fitting percent. If you look at the impulse responses of the second order, third order, fourth order, they are kind of similar in the response. All right, but it is significantly different from the first order estimated model. All right, you can take a look at the you remember the impulse response? This is h of k. I plot the h of k. What is h here? The impulse response. This is the time domain in the discrete time manner when you take the z transform, the inverse of the z transform back from the transfer function in the discrete time. Okay. All right. Here's the example of the code. In system identification toolbox, data are stored in a manner that is stored in the manner that is called system identification object, and that can be used by the command ID data. So you need to specify input and output. All right. This is kind of always a pair of input-output data. Using ID data, it will convert to, as I said, the data in system identification format. Okay. And then if you keep the data in this format, you can just call many algorithms, many estimation method in this toolbox. Okay. Here's some example. I keep the data in this mat file in this structure, and then I load it. I create the model as a cell of 4 by 1 because I want to vary the model order from n equals 1 ... n equals 4. I use the command n4 SID, all right, and I specify the data. I specify the model order. I assign each estimated model in the cell. SS model, each index k, this is the system object. This is estimated system that contains A, B, C, D, contains everything, all the information about estimated model. Okay. And after you estimate it, you want to compare the fitting, you can use command compare. Compare requires data set you want to use. This can be test data set as well, validation data set. But right now, I just use the training data set as I use in the estimation process. And the rest of them, this is the list of model you want to compare. So the command is very convenient. So I compare the 4 models at once, and that's how I get these pictures. Simulated response comparison. Okay, and then before the step of getting the model, as I said, sometimes you need to pick the model order first. To get this GUI, I use the command n4sid, specify the data, specify the range of model order from 1 to 10. Okay, and here you can specify the input delay. If you already know that your system description has a delay, 2 steps, 3 steps, or what, you can specify the number. Okay, so from this command, if you pop up the GUI and then it hangs for receiving your input, which is the model order you want to pick. Okay, so after you pick, it will estimate and store it in MNS variable. In the second example, mass spring model. This is a very simple system we learned from physics, right? Here's the thing. You have mass, you have spring attached to the mass. You apply force. I use the variable u, okay? And at equilibrium, the mass is rest. The mass rests at this position. So as you pull the object, pull the mass to the right hand side, and of course it depends on your u, the waveform of your u, and then we measure the displacements from the equilibrium point. We know that the system, when you derive a dynamical equation, this is the second order model. Oh, I think we assume to have some damping as well. This is a friction with the with the parameter c. Okay. The variable y is the displacement. Okay. Here in this slide, I would like to illustrate an example, the flexibility of estimation method, that when you have some structure in your state space matrices, just like in this case, this is your A, this is your B, right? This is your C. You kind of have the structure that your A contains 0 and 1 here. And this is some parameters that you don't know yet when you estimate, but you kind of only want to estimate these two parts, right? And you want to pertain this structure that A is contains 0 and 1 in the top row. I hope you understand how to get the structure of A and B and C. Just review these equation real quick, all right? And you know that kind of review how to get the dynamical equation of this mass spring model as a second order system, and then review how to transform into state space equation. Okay. So the goal is, of course, you can estimate the model without assuming anything about the structure. And the second option, you want to estimate the model that you want A, B, and C to have this structure. So I consider 4 choices of the models. And I would like to mention that when you estimate subspace, when you estimate state space models, in system identification toolbox, it has SSEST, state space estimation. It also has this command. This command is different from N4SAD in the sense that first it will initialize an estimated model by a subspace approach, which is N4SID, but then it applies, the algorithm apply iterative methods to refine, to adjust the, so here at the first step you will get A hat, B hat, right, and D hat. as an initial model, but then it will update the system parameters using prediction error method. It will update to the system to minimize some cost objective, which is a loss function defined in PEM. All right. So the results of SSEST is supposed to be better in terms of the performance of the fitting. Here we compare 4 models. Discrete time model using N4SAD, discrete time model using SS estimation. Okay, by using the model from the first choice as the initial model. Okay, the third one use continuous time. The thing is, this algorithm, this command, can also estimate continuous time model directly as well. So it will transform back to the continuous time for us. Right? And the last one, this is the one I would like to mention, which is continuous time structured. So we're going to estimate continuous time using SS state space estimation with the predefined structure. So I'm going to specify that I want ABC to have this structure as I derive from dynamical equation. So let's see the results. So for the mass spring system, I generate again, this is my U, this is my X, sorry, this is my Y. My U is PRBS probably, and my Y. When I okay, this is the result again after the fitting. I compare the fit percent. The gray one, which is kind of not very clearly to see. This is the measurement Y, okay, and the rest is the estimation. You will see that the one from the N4SID, which is the blue one, the fit percent is very low. It's kind of it doesn't track the gray one at all. Okay, this perform a little bit, not a little bit, perform poorly in this experiment. And for the rest of the rest 3 models are the fitting is very very high. Okay, so as you can see, if you use SSEST command, it refines the model, so the performance is are very better. Okay, the system matrices that given by the default SSEST are typically dense, which means your A matrix is gonna have all the non-zero values in all entries. Okay, and for the CT structure, as I said that it will have a structure as we specify. This is the example. Oh, I don't have the example here, but this is the true transfer function. This is the continuous time transfer function given by SSEST command. So this is the CT structure. Okay, so when you look at the transfer function, you see that this one it doesn't assume any structure in A, B, C, D. All right, so it has some small value in the coefficient in the numerator. These two guys are very close, and if you compute the poles, all right, so I have 4 sets. The first one is the poles of the true system. The second one from CT SSEST, the one with the dense structure, and the last one is the one from predefined structure. So the locations of poles from those 3 models are not significantly different. So in terms of the response, that's why you see the fitting and the response, these are close to each other. Okay. But the one with the structure give you kind of maybe a more meaningful system parameter if you want to contain, if you want to use ABCD in that coordinate. Okay. This is an example of the Matlab code in this experiment. Here I didn't vary the model. I specify at order 2 for initial model and for SID. Okay. You use N4SID command. For the one estimated by SSEST, okay. Hold on. Yes, okay. SSEST command, this is estimate. Hold on. This command itself, it will, so you need to specify the sampling time so that it recognizes that you want a discrete time model. Okay, you can assign the name as well. And that is the discrete time model without assuming the structure. And again, it will, the performance will be improved from MN4 because it's refine the estimated parameters using the PEM. Okay, if you don't specify the sampling time, the SSEST command return continuous time estimated state space system. For the last one, this is the last one. If you want to specify the structure of A, B, C, D, okay, you assign, you create a variable init system. You use the command IDSS, which means you're going to create a state space model with a matrix A, B, C, and D is 0 and everything. I don't remember now what these are zeros. You can just check the manual. And then I specify that in the structure of A, okay, this is I mean, because the indices is a structure variable in Matlab. So if you go to the field structure, go to the subfield A and free, this is to specify which entry should be the free parameters. Okay, so if you take a look at here, okay, in A, which one is a free parameters? Napat, which entries?
The row 2.
The second row, right? So it is 1 position and 2 positions. So that's why you specify such a way that the top row is false, not free. Let's fix, right? Let's fix to this value that you already specified previously. And the second row, true, free. All right, the values of the free entries, these are trues. And the same goes with the matrix B as well. In the matrix B, let's take a look. All right, so you want it to be here. You want it to be free, right? The second option, the second entry, and why the first one you want to keep it fixed at 0. So when you predefine, okay, your matrix B, you predefine 0 here, you leave 1 here, but in the second entry, you leave it to be free parameter. Okay, so for the matrix C, you want it to be fixed. That's why you keep everything false. And then you use SSEST command using the data and specify init sys, okay, that you already put information here, and that's return the CT structure. Okay. Oh, I think I know. The parameter 0 here should be, I think it's the sampling time. When the sampling time is specified as 0, it means that your model is continuous time. Okay, and that's, so when you specify, you already specify the metadata about your system. everything is kept in this structure variable. Continuous time, structure of A, you know which entries are free. So when you specified it, it will calculate, it will estimate the model for you. Continuous time with the structure. Okay. So here's the example of numerical implementation of subspace methods. In the next video clip, I will explain the mathematical concept of this one.